Pull over your class docs repository, and we have a, oops, gotta get my overhead thing down here. But we have, there's some new slides to go over. We're gonna finish up the slides that we did today, or sorry, that we did on Thursday. We're gonna finish those, and then once those are finished, we are going to go into some new slides, which is kind of more of the same. I hate to say that. I know that doesn't sound very interesting, but it's more of the same, where we're going to be doing more. Today we're going to be finishing up the singular variables in regression, and then we're going to be talking about multiple regression, which is actually quite interesting because, as we were talking about when you're working on a model, it's not always the one variable that actually influences the model, but maybe it's a collection of variables. So we'll talk about that and see how much we can finish today. Anyhow, so please do pull up your repository and get ready to rock and roll, because I think this is going to be just extraordinary. Except, it looks like it's not always. Well, I guess it's okay. I'm seeing that maybe, sorry, just the screen here looks like it's not exactly as wide as it could be, but I guess that just happens, doesn't it? Okay, so, here we go. I can probably do a page fit, and that might fit things. Does that make any difference up there? About the same? It's about the same. Okay, anyway, but still, where were we last time? So I'm going to go kind of fast forward thing. I'm going to fast forward through what we did last time. We're in this slide deck here from week 9. I'd like to finish that up today. But we have the 29th of October, and let's see, we are going through. I believe that we ended up where we were talking about, for instance, some of these models here. One of the big important things that we did talk about, though, which I don't know if I stressed enough, hopefully I did, and that is that I stressed the notion of this thing here called the RSS, which is the sum of residual squares. Now, this is your measurement from how far away each of the points lie to the actual kind of what they call the expected point, or the line, the expected line, I guess I can call it. But really, this line here is where these points should have fallen according to the expected calculations of the statistics behind behind the regression or linear models mathematics here. But one thing that I did talk about, though, is that when you're looking for models here, if I have two competing models, go for the model that has the. If you're looking for a tight, oh sorry, I should probably say something here. But if you're looking for a tightness of fit, that means you want to have all the points landing as close as you possibly can to the model that you're actually producing. In other words, that when I make a prediction here, I want that prediction point to land as close as I possibly can get to where the points naturally would have fallen. Then what I want to have is a model where I have a very small RSS number, and you can see in the graph right here, the upper and the lower graph, you can see that in the upper graph, on the y-axis, you have a very small difference between where the points land and where the predicted line should be. It's very, very small. You can see that from the y-axis. However, when you look at the y-axis on the lower graph with a much larger RSS value, you can see that there's a lot of play between where the expected line would be and where the actual points fell. And so that means that there's a lot of flexibility, if you will, between where the points could possibly land. And so that means that your model isn't going to be very precise. And so if you want to have more precision, then you'd probably have to go after a model that has a smaller RSS. Anyway, but of course, this all depends on the data that you have, and sometimes you have no control over that number because you're working with the data that you have in your hands, and that's all you can do. You can't grab any more data. And so that's something to think about. And so sometimes you have to just kind of work with what you've got. And so, but if you do have the ability, though, to choose, I would say, try out both models and see whether one model works better than the other. But now that you have these, you have an RSS value here, maybe that would be something you can use to help you to choose which model it is that you would like to go after. Anyhow, that was just a big thing. I think what we're talking about today, though, is we worked with this crime data set before, which was actually quite interesting. All the code is here. I do hope that you've been spending some time looking through this code. And we made these interesting plots. This actually was a plot that we created where we used the linear model. So this line that we created was actually our linear model. And what we discussed here was that these points that we see on this plot here all these points, we use to create this linear model. That means that, for instance, if I wanted to see what happens about when x is equal to minus 30, what does my y look like in general? Actually, my y would be about, oh, I don't know, 3,800 perhaps, in there somewhere. And so that would be about where the points would land. And so my model would predict that kind of point. Now, that's all very good, but one thing that I mentioned, though, that many people, I claim, and I'm pretty sure that I'm speaking for the for the masses here, but one thing that I've noticed that many of the analysts in the literature tend to get wrong is that when they create a model just like this, the model in this case is defined between minus 80 and about 10. That's where it's defined, and that's where you know that you're correct. Now, it's mathematically possible to start throwing in any arbitrary value of x into your model and see what happens, and that's perfectly fine. You can calculate a value. But will that value that you calculate actually be relevant? Is it actually creating a value that you can use? And I find that in many of the articles that I've read where they've used models to make predictive analyses, they've gotten it wrong. And for instance, here they'd use a model like this between 80 and 10, and they'd say, according to our calculations at 500,000, this is what we would find on our model. And while you can still calculate a number at 500,000 for x, it does not mean that that number actually is going to, or that model is actually accurate at 500,000, because you have no data that trains it. And so what I'm saying is, you have no data that trains it at that particular window of on your x-axis. And so what I'm saying is that when you create a model, you have to make sure that you're actually using it appropriately. Is the point that you're throwing into the model to do a test actually inside the range of the data that you use to test that model? And if that's the case, then fine, use it, use the model. But if the point that you're testing, or you're trying to make a prediction about, is not inside this data range, then that means that you're probably abusing, that's right, you're abusing your model, and you're not able to produce anything that's reasonable, or any kind of prediction that could be that has any credibility. And so you find that there are a lot of groups that will make a model like this, and maybe the model that they created, where they used code like this, where the model actually was correctly made. It was actually they designed it correctly, the data was correct, but where they're actually producing results, like where they're predicting, is just off the scale, and so that's not, it's not right. Anyway, these are we talked about this code here where we were able to actually create a model where we're looking at how much the temperature of a certain place may influence the crime. This TC 2009 was a crime rate. We'll have to look into see exactly how that number was created, but actually it's a number, though, which has to do with the amount of crime. And when we created our function, when we created this right here, this mod, LM is our linear model. When we created our linear model here, actually what we were doing is just creating a function that looks exactly like this, where the x was a value that we could predict and throw that in and see what happens, with our on a particular point of x according to our model. So anyway, that was very, very interesting here. So we had these. Let me just move into the next thing here. So we had to deal with where is it? These are the coefficients. Well, anyway, when we ran our model, we came up with these coefficients, and these are, for instance, the intercept is the point where at x is equal to 0, that's where your y is going to be crossing. That's what your y value is going to be. Where does y cross over? At x equal, when your x is equal to 0, this is where your y is going to be crossing. And so then this low value that we see here, that was your slope. In fact, we would put those into our line equation right here. So we have the alpha, which in this case is supposed to be our intercept. And then we have our beta, which is going to be our slope. And then anything else that you have, like your error, would be your epsilon. Anyhow, so this is where we're actually talking about using the model. This is where I'm actually throwing in a value of minus 10, and I come up with this value here of 40.86. And let me just tell you that this value is a good value to try in the model, because going back to what I was saying before, this is still within the range of the data that I use to train the model. However, if I'm using like minus, some bigger number, then that's outside of the data that I used, outside of the range of the data, and so therefore it wouldn't be a good number. I could still come up with a number here, but whether that number means anything, that's debatable. Anyhow, these are just using predictions. That's really what the prediction idea is. We're just throwing these values in and finding out what our model suggests will happen. I do apologize for all the noise outside the window. We have a leaf blower just outside our window, and it looks like an ambulance is going down the road here, and so it's kind of noisy. So if you can hear that at home, then I'm sorry about that. One last thing that I talked about here was, and this is just to get everyone caught up here so that we can go through today's code, is we have to ask ourselves, do we want the intercept value in our data, in our model? Does it make any sense to have it? And so here we have to use this called the intercept terms, alpha in this case. Alpha, y is equal to alpha plus beta x plus epsilon, or y is equal to mx plus b, as we might see now in an algebra book. But that alpha here is the intercept. It's the value where, in fact, I'll just go back and show you. It's the value here, 4256. So we have to ask ourselves that when we're creating our model from all this data, do we need that intercept? Is it necessary? And so you have to use your talent here. You have to, I would say, plot the data and see what it looks like when you plot it with the intercept and then without the intercept. And so I guess this is the best way of saying it here. Sometimes the y-intercept is relevant and sometimes it isn't. And this is, I guess you can say that here, there's no meaning for the y-intercept. I'll just read this. When the data is not present near the point at which the x is equal to 0. And the model suggests the data is present at this point. And so, for instance, here we have the data is not present where y is equal to 0 and x equals 0. So it's just not present down here. And so why would you want to, on the right-hand side here, it doesn't make any sense to have a model that looks like this. But also, that's a mathematical expression. But I would say that I'm more of a visual person. And so when I'm deciding in my models whether I should use the intercept or not, what I do is I look at the data points and I see whether, for instance, in my mind, I could actually add a line in my data set so that it skewers the data exactly as I see it on my screen. There are two ways of skewering the data. That means there's two ways of actually inserting a line, one with the intercept and one without the intercept. And I look at the data and I think to myself, does it make more sense to use the model and the line on the left, or does it make more sense to use the model on the right? And by doing that, I think to myself, does it seem like more of the points have been kind of used to align the line than in one graph than the other? And when I look at this particular point or this particular plot here, I'm convinced that using the intercept at the left-hand side, that more points were actually involved with creating that line in the data. Whereas, for instance, when I look at the line on the right-hand side in that data set, I think that fewer points were actually involved with creating the direction of that point, or of that line, rather. And so it just comes down to looking at the plots. And so that's why I keep telling everyone in this class to just plot, make as many plots as you possibly can, and just to see what it is, because this is exactly how you're going to be, this is how you find your results. You plot everything out, and then you decide, well, actually, this is a better way of looking at my data than otherwise. But the thing is, though, that in R, it's very easy to make your plots. So I'd recommend just to make as many plots as you possibly can, especially in this case, if you're trying to decide whether or not to keep the intercept or not. Yes, sir?
So I guess when we have to look at whether the weighted line touches the y-axis, what do we think it looks like?
I would say, so the question is like, what am I looking at again to work out which model is to pick? I tend to be more of a visual person, and so what I'm doing is I'm looking to see on the left-hand side here, see how those points are kind of like, they're already moving in a kind of a sweep like this, and the line seems to actually conform to those points better in that particular case. Then on the right-hand side, where, sure, you could argue that the line does sweep through those points in that, declining direction on the right-hand side, but I'd say that a better line could be drawn. And so in that case, you just have to like eyeball it in that case. But you're saying that is there a better line out of the two models that I'm creating here? Is there a better line that I could draw? And that is really, I think, one of the best ways of doing this. But mathematically, though, you're asking yourself, where was it? Whether, for instance, the data is present near the point where x is equal to 0, and the model suggests the data is present at this point. So you can see, for instance, here on the right-hand side, getting back to your question, Alex, the model here, remember, the line is the model. The line is suggesting that points are there. But on the right-hand side, this line is saying there are points that are around the x equals 0 and the y equals 0. There are points there. But actually, when we plot the points, we don't see any points there. So the line is actually taking us through places, or suggesting that points exist in places where they're really, really not, around the origin of this plot. It's a very complicated thing, I think. But to actually go through all the if you're creating an algorithm to actually determine which plot makes more sense, like how do you actually determine whether it's better or not? But I think that what you need to do, though, is just look at both plots and see whether the line is in a reasonable space, like is it inside the area where you're plotting. So here the data is between, I'd say, -60 and, I don't know, 10 perhaps. And so we have between that area, I would say that about 3/4 of the time on the line, it's suggesting that points are there when actually the real points are not there. Does everyone see that? No, I don't see that. And so then on the left-hand side, I would say that most of the time on the line, it's the data is suggesting that the line belongs there, whereas you don't have many areas of points to suggest that the line should be there on the right-hand side. Anyway, it's but I would say that still, just to make sure that you're right, I would say plot both of these things. Let's see what it looks like, and then see whether you're convinced. Are you convinced, you, the data scientist, are you convinced that line is the best possible line you can create that actually goes, that skewers that data? I would say that no, the right-hand side is not, because the line is suggesting that points are found in places where they are not. Whereas on the left-hand side, the line is suggesting that points are found where you could argue that the points are really found, that they are found. Anyway, so just plot them both and have a good look. When you see things visually, it's always easier, I think. That's a good question, though. Thank you. All right, let us move on. I think I'd like to move on to the big question that we're about to. Oh, here's some more intercept. You can always this is how you actually plot the intercept. Here, for instance, that's testing. When you're actually working with a model, you have this piece of code up here where you have this tilde1. This actually adds the intercept. I mean, you don't have to always add that 1 if you don't want to. You can always just have this, and then plus. Actually, no, sorry. You have this and this right there, and then you can kind of remove this 1 plus right here. You can remove that part, and so it's just really this tilde and then low, and that would be your model. This plus, or this 1 plus, actually does create this. It's actually telling R, be sure to include that intercept. But I think it's already included by default. However, if you wanted to remove that intercept, then you'd have this -1 that appears. And -1 is actually going to change the actual, you can see, for instance, if I move out here, it actually changes the plot quite significantly here. I guess the only way that you could really see which one of these work better with the data is to actually throw the data on the screen here. I don't have the data to obviously plot it in the background here. But if you had the data points actually plotted along with this line, then you would see which line is better, whether it's this one where I include the intercept, or it's this model here where the intercept has been removed. So the line by itself is hard to determine. I would say plot the line with the data. Anyway, hopefully that helps. Okay, I'm going to move on now. We discussed the model, the summary. This is actually a very important thing. Once you've actually created a model, typing in the word summary followed by the model variable that you created. So for instance, if I created a model here, this is right. This is the module no intercept. That's actually that's not just one variable, but that's like seemingly all the variables that have to come out or that have come out of my linear model. And so if I type in summary, just like I do here, if I type in summary, then that means I get all the information that describes how my model is performing, including at the very, very bottom right-hand side, I have my p-value. Now this is such a small value that I'm going to say that the model is good. That means it's dependable. Now, whether or not the model is good in terms of making accurate predictions, that is another story. That story is really dependent on the variable, or sorry, the data itself, and other pieces, including, I mean, there's maybe other variables that you haven't included that if you put them into your model would make a better model. That's all debatable stuff. But still, though, in terms of how this model was developed and how it came out with this particular data set, it seems like it came out quite well. The p-value is good, which means that you can give this model some respect, if you will, and it seems like it's dependable. But looking at right above that p-value, I'm looking at the adjusted r squared, which I see as basically 0.25, which means that I would say, remember, there's the scale for r squared. That's that's between -1 and 1, and what that value means is how good is the dependent variable explained by the independent variable? How well does that work out? Well, this is saying that 1/4, or I guess there's 1/4 of explanation here, but there's maybe 3/4 where something else is missing. Something's missing from my model to fully explain my dependent variable. So in this particular case here, remember my model is looking at the temperature, and we have this value here talking about the amount of crime that happens in an area. And that is a very complicated issue. Crime in areas, crime in towns, crime in town or in cities, crime in countries. That's a very, very complicated issue here. And so it's not surprising to me that this is saying that actually this model isn't very informative, although it's well developed and it has some credence. There is so much missing from this model that it shouldn't be taken like ultra seriously because it has such a low r squared value. Anyway, and you can still use it as a model, and if you did use this as a model in an experiment of some kind, you would have to keep saying that according to the data that I used with this model, and then these are my predictions, and then you'd have to talk about, for instance, some of the, I guess, how the model doesn't perform as well as it could do. You'd have to describe the faults of the model so that the people who are listening to your talk know that there are faults. This isn't a hard and fast rule, but there are faults. And you'd start by discussing those faults by mentioning the r squared value. So that's this. And so, for instance, if you have an r squared value of 1, it means that your independent variables are predicting the dependent variables. And so that means, like, for instance, my favorite example in this class is, what about the more time you spend studying, the better your grades get. If you ran an experiment like that, where you started collecting data, and you found that more people, or the more time people spend studying, could that somehow influence better grades? I think you'll find that as a rule of thumb, that does work, but I don't think that your r squared value would be very high, namely because it's not just about studying that gives you good grades. It's about maybe your mental health, the amount of exercise you get, the amount of sleep you get, your support group, whether or not you're stressed out. Does your family members continually calling you and bugging you about things that you have no control over? I mean, that actually happens. Are you stressed out by things that have nothing to do with campus? Do you watch sad movies and spend all your time thinking about how sad the movies are, and even though you're spending time studying, you're actually thinking about the movie and how sad it was? I mean, these are things that actually I hear as a teacher here, that somebody said that they weren't, this is like 2 semesters ago, somebody said that they were part of the film club here on campus, and they had to choose movies for the film club's upcoming movies that they were doing, and they were going through a state of panic because the movies that they were watching were just too much for them to take, and it was really, really scary. And so I said, well, I'm sorry to hear that your grades are being swayed by these movies. Could you not offset some of this some of these movies to watch to some of your colleagues, and so they did. So anyway, what I'm saying though is it's not just the amount of time that you spend studying, there's other things. And so your model that would reflect that. You would see then your R squared value that there's something that's not as high as it could be. Anyway, this is just more stuff you can play with. I think that this is another model you can play with, you can see. But this is another one I wanted to play with today, another model I wanted to go over with you today here, and that is what influence is there on earning potential and personal height. Now, this is actually a very important question. Many people have actually gone after this particular question. They say that the taller you are, does that mean the more you make? And so let me just go ahead and start up my code here. This is the code that we began, I believe, last time in class. I'm just going to start running all this stuff here and just get that's all caught up to where we were. Oops. Now I have to load my data set. You can't see what I'm doing now, but I'm actually going after the data that I'm supposed to look at. The first one we're going to go through this crime, and I'm going to go through the wages. So we have these things coming up. There we go. I was creating my mesh. I want to make sure that my models are actually going to come up here. So this is all the crime stuff. Hopefully you have some of this stuff already recorded someplace. You've tried out this code and you have it on a source code. The next thing I'm going to be working with is, if you can see, I'm going to be opening up the wages data. And if I can find that it's here, there we go. And what the wages data is all about, in fact, I'll remove this so that we're not confusing ourselves with which plot is which. But the wages data is, hopefully I can get this to work here. Let me just talk about that data for a moment. Where's it lowercase way? There we go. So this is what we have then. So for our wages data, before you do any analysis here, you want to spend some time actually looking through the numbers and making sure that you know what's going on. But we have the, I'm looking at the age. I have ED, which I think is some kind of education. I'm not exactly sure what the scale for that is. I'm thinking that the higher numbers, the bigger the numbers, the more education the person may have. Maybe it's like maybe it's like, 16 is like 16th grade, or that's their senior year of high school. Maybe 17 is the 17th year, so maybe that's like college, some college, I guess. Anyway, but then we have the race, we have the sex, we have the height, and we have the earning power. And I think that probably what we're looking at is the height and the earning power of our particular research here. I can see, just looking at this data, that there are some errors. I don't know how it's possible to have somebody who's actually negative height. I don't know how that happens. A negative 95.71. Now, I would anticipate that perhaps, I would think that perhaps that negative value was someone pushing the wrong button when they were entering the numbers in. Maybe something was erased. Could be anything. But I would say that that is probably a mistake. And some of these other values are like, they seem almost like they're just too small. I mean, or maybe this is like the earning power. Maybe this is like, I mean, how can you make less than, how do you have a negative 95 unless you're in chronic debt? So that I would say that there must be something, either a mistake or something that needs to be explained to us. Anyway, but still, what I will start out with though is, we started out looking at the correlations between the earning power, the earning here, and the height. Now, remember the code that we used to do this is that here we have wages. And when I have wages followed by this $sign, that means that I can actually say, use this data set, but find this column. That's what the $sign does. Let me show you. Wages, $sign. When I put a $sign there, can you see that? Here we come. You can see now I can choose the columns that are in my wages data set. So I can go after height. Press enter, and this is my height detail. You see? I can remove that, and I can go after, let's go after education. And there we go. This is the educational detail. Now, sometimes on your machines, you might find that it doesn't show you everything. It will just show you 3 different dots, like here, for instance, and I would say that there's more data, but it's not showing you everything. Anyway, so getting back to the actual code up here, that's how we're going after these columns. And so this is a correlation where we are looking at the earning power, which is this directory, or this column here on the extreme left, and the height, which is the second over from the left. And so we're looking at the correlation. So that's kind of where you want to start by saying, okay, well, if I'm doing a model, what kind of correlation do I find? And you can find that, for instance, here we have this correlation of 0.29, which I guess isn't bad. It's not 0, which means it's not like it's nothing. There is something. It's loose, but maybe there is something there. And then we have the opportunity now to actually do a plot. So here we have the wages. I'm going to do a plot where my aesthetics function is saying up for the y, so my x is my height, and my y is my earning power. And I get this plot, which is kind of hard to see, but it's down in the bottom here. So if you can see that. So that's actually a very interesting graph. But one thing I should tell you, though, which is kind of interesting, is that while that's interesting, let me just show you something. I'm going to copy this. What you could do is you can change out the y and the x. There's no reason why you have to leave them as x and y. You can change them around and see what happens if I change out my x now to be height and my y to be earning power, whereas before, remember that my x was the earning power and my y was height. That's perfectly acceptable in analytics here. That's perfectly acceptable because, I mean, we're still doing back of the envelope types of calculations, and we haven't quite decided whether one thing is influencing the other, or whether they both influence each other in some way. It would say, this data would suggest perhaps that the earning power is maybe the independent variable, and the height is a dependent variable. Maybe there's something there. Of course, you have to change your argument each time. You'll have to actually figure out how to explain these things. But in terms of actually looking at the graphs and plots, you do get an interesting story. This is actually what I'm kind of talking about here. Look at this. Before I move on any further, look at the line, if you would, in our graph. On the left-hand side here. Notice how where all the points are gathered between, I guess, around the 0, e plus 0, 0. That's just scientific notation. It means that we're around x equals 0. But you can see that where all those points are located, there is a very slim shadow around the line. Whereas as the points become more spacey and more spread out, then we have a bigger shadow. That shadow is the 95% confidence interval. And that's suggesting that I know that this model is correct because it's been trained from a whole bunch of points which suggest that this is where they like to gather. So my predictions would be accurate using this model where I have a very slim shadow. I know that the points will show up on that line somewhere. However, when I move out to the right-hand side of my plot, I have fewer points, and so I'm a little bit unsure about where those points could fall. They would have to fall in that shadowed region somewhere, but I'm not exactly sure where. And so when you're looking for a good model, you want to find, I mean, if you're making predictions here, this is suggesting that your predictions, any predictions that you create between the 0 and 1e, between that first block where the points are, the predictions there would be much more accurate than the predictions anywhere else. In fact, as you go out to the right-hand side, the predictions get more and more poor. Anyway, though, but still, you have that ability now. So you should just look at all these different plots and see what you can see when you just plot everything. Just see what maybe you'll find that there's a better model to make. In fact, this model here looks like there's a very slim shadow around the blue line there, and so that says that really anywhere along the line is a good prediction to make because we have enough points to say to show us where there's to guide our prediction. In other words, we can train our model very, very well here. We have enough points. But still, this is saying, though, this graph here is saying that the height as an independent variable is, well, I guess you're saying the earning power and the, there is some kind of a thing here. The earning power does seem to have some kind of correlation with the height, but it's not a very strong one. And the line is gradual, but there is one there. There is one there. So anyway, I'm going to move on now with the actual model that I'm creating, which is this part right here. And so if I just go ahead and run that, I have R mod. I can look at my coefficients, which is this code right here. But I can actually see what the intercepts would be in order to create my model. But one thing I will say, though, and let me just go back to my slides. If I can find my slides, that would be just terrific right now. One thing I will say though is that when you're working with your data, um, here we go. You have to realize that you'll find that it's not always perfect. These outliers that you may find here, you see, if I can compare both of these lines here, you'll find that there's a line um, on the left-hand side. The line kind of goes through, and then it has a kind of a hiccup around x equals 7, or sorry, x equals 70. That kind of hiccup there is because of the outliers there. So you have to always remember, though, that when you're working with data like this, these outliers actually do cause problems, and they will change how you see the actual result. And so I would recommend that before you go through and actually start declaring your model to be a winner and going through and talking about how it's predicting all this amazing stuff, please do take some time to go back and kind of revisit the data to see whether if there isn't anything going on in the data that's somehow influencing your model. I mean, can you explain the data in terms of the model here? Anyway, that's just to be on the safe side. And then, of course, you have the correlations and other things here you can use to kind of determine whether or not the model actually is, or actually if the data really does seem to be good. If one thing does seem to influence another. In other words, does the model actually make any sense? But what I was going to say, though, is that here we are. So when we typed in our command, if I can get back here, where was on the slides again? Okay, so going back to the slides here, when we're actually when we run this summary command right here, we get to these coefficients right here, coefficients. And so we found those same coefficients actually in our, I can get back over here, we actually found them inside our model by typing in this coef command right here. And what this is going to do is it's going to actually give you the coefficients of your model here. Now this model is becoming a little bit more interesting than the other model here, where we've broken down our model into into earning power and race. Now this is becoming this is a kind of a controversial thing here, but you can see that by looking at the data, just going back to the data, you can see that the earning power, you can actually aggregate your earning power according to the different races: white, Hispanic, and I think there's African American and some others in there. Other white. Let's see what we have here. We have Hispanic, we have race, other, and we have race white. So anyway, but you can actually see the earning power. It's not just in this data set just about height, but you can actually see about the races. And then because we've looked at the model here where we're looking at the earning power and race as a model, then each of the categories that we find in our data actually now get their own coefficient. And we can find those coefficients by typing this coef r mod, which is the name of the model that we used. So remember what we've done here, though. We've taken our race, which are the independent variables, and the independent variables now in the model get their own get their coefficients, and so we can see those coefficients. And now we can make a more complicated model than just a model where we have height and earning power. And so that's really kind of what we can do with this data. But it all depends on how much data you have, depending on what you can do with it. So going back to my slides, what else can we do? Let's see. We find, for instance, that when we take all these numbers out, let's go ahead, here we are. When we take these numbers out, we can actually create a more exciting model. And this model actually might be better. In fact, I can just find something here. Let me see what the R value was for that. I'm going to go back to this. Hang on, let me do my summary of this model and just see what it is. What was my model called? R mod. Okay. So my R mod, the p-value is, remember, the p-value isn't so small. In fact, some would argue that this model is not very good. And I would agree with that, because I think that there are many pieces involved in a model of, in a question about what different types of different kinds of communities make in terms of earning power. I think that that's a very it's a very loaded question here, and there's many factors involved. And so what this is saying is that when we have this, we can spread this out a bit here. the R value is a pretty small value. And so it's saying that actually, yes, we can make a model out of this information here, but there are many, many more variables which we ought to include to get a better picture of what's going on. And I find that the reason why I'm actually putting this into our slides, if I can go back to the slides themselves, is because I find that many researchers, in some of the papers that I've read, are looking at models where there's not enough information in there, and so we don't get the full story. And this is one of those things here. And so this would suggest to me, though, if this were my research, to go back and find more data, to find out more about the truth. But I am still convinced, though, by looking at these numbers, that there is a difference, that there is some trend to find. This is telling me, for instance, that the earning power for different ethnicities is quite different, and that I believe, and that's unfortunate. I feel that that's a fault of our society. That is but here we have a model that actually shows that. But in terms of actually being able to hold up and say that we know everything about this problem, we don't have that in this model. We cannot say that we know everything about this problem because we don't have a high enough we don't have a high enough R squared value, and we don't have a low enough p value. And so while we are convinced that there is a trend to be discovered here, we have to find more data, and maybe to reduce our data and actually concentrate on specific areas in order for the general research public to agree with us. They'll find some way of saying that our model doesn't count, and therefore this research that we're trying to share with the world won't make its way out there because people will shut it down. And so what I'm trying to say, though, is that when you're working on your model here, please do make sure that before you start talking about all the stuff that's there, make sure that it's tight. Make sure that you have everything there that you need. Otherwise, people will shut it down. They'll say, "Oh, we don't know what you're talking about. It's not the p-value is too high. The R squared value is too high. It doesn't hold water." But that's really that we don't want that to happen. I am convinced, though, that these numbers are showing something different. And you can see, for instance, here that they are numbered. The intercepts are different. The intercept, for instance, for an African American or a black person is, let's see, 28,372. Whereas if you move up to 28,372, you can see these values are different for different types of nationalities, which means that they're not making the same money, and that is a shame. I will say something else. This is not a political science class. I'm hoping that everyone here is able to draw their own conclusions over the data that we cover. But I would like to say, though, that the data that we see here, this is a kind of a panel, if you will, where I have used facet wrap to plot up all the different pieces of all the different earning groups. We have black, Hispanic, other, and white. You can see that the lines are different. You don't need a model to tell you that the lines are different. These lines, remember, each data point is talking about a person and how much money they make, and that person according to what their community is. And so you can see that there's a lot of data for white people. There isn't so much data for other, and there isn't so much data for Hispanic, and what does that also indicate to me? That indicates that perhaps these groups are not being asked what they're making, or they're not being given the opportunities, or they're being marginalized in some way. And that is something that I think that we need to work on as a society. But I can tell you, though, that I'm disappointed to see how little data that there is. If this is the exhaustive set of data that we have on the subject, then this would be just a travesty, because we would need to find much more data to be able to actually handle or to understand what these problems are, what's going on. Because we have so little or so few points in other and Hispanic and black, it makes me think that perhaps these societies were not consulted, and that's intrinsically wrong. So anyway, what I'm trying to say, though, is that what do these plots also indicate? Just looking at the number of points suggests to me that somebody isn't asking enough questions. Anyway, that's enough. are there any questions over this whole? Are there any questions over the any of these slides here? If there are, then please ask them now. Otherwise, I'm going to move on to the next slides that we have. So these slides are going to be slightly different than what we were talking about before, where we were working at first with just one particular variable, and then we started working with more than one variable. And one of the big points that I was making is that when you're working with a model here, sometimes you find that one variable being studied for its influence on another variable is not always enough. Even in simple examples where, more study time equals better grades, that doesn't mean anything. And that is because there are so many things involved. So we are actually looking at different types of tests where we can actually include more than just one variable, because sometimes we need that. So when we have just two entities, then you might find that there's more of an influence you can measure on the dependent variables. Anyway, so here's the thing I was actually kind of getting on about before, is that, for instance, the GPA or your grades you get in school would be dependent on studying, but maybe also a bunch of other things too, like studying, rest, food, and some other stuff. And so we use this new system called multiple linear regression to actually put in multiple variables into a model to see whether, for instance, those model or those variables work collectively to influence our dependent variables. And you can do some analysis to see which of those variables actually are doing the best job, or which are maybe you'll find that some variables are not actually useful. They don't need to be in the model. We don't actually talk too much about that here, but actually there are whole books just based upon whether or not those variables should be in your model. Should you take them out? Do they not meet some specification that you need? So anyway, though, one of the kinds of questions that you might ask where you need multiple variables are, for instance, age and IQ scores effectively predicting the GPA. Now, this is a very loaded question, and I think that if we all thought about the how do you predict GPA, I think we could all come up with very different ways of predicting GPA. And so you can see, though, that a kind of question like this, where you're working with multiple variables, actually would be an important type of solution to finding out whichever those variables were that predicts GPA. And so it's not just one variable, but it's several. Here's another question you might ask using multiple variables. Do weight, height, and age explain the variance in cholesterol levels? That's true, but I can think of something else. How about exercise? How about if you, I don't know, if you eat a lot of junk food, if you eat a lot of meat, if you're a vegetarian? Does that make any difference at all in your cholesterol levels? And sometimes, in some cases, it does, but in other cases, it doesn't. And so you need to have as many variables as you possibly can in some cases to actually check to see what your cholesterol levels look like, because there are so many things that could influence them. Could video game sales be explained by exciting graphics and inexpensive costs? Is it something else? Is it the game itself? I mean, what else is it about the game? Is it the story? And so I think that we all get the idea that there are some questions out there which are really, you can't just answer these questions using like one variable. It just doesn't work that way. Road safety, for instance, is that a combination of relaxed or defensive driving? Are there more independent variables to be used to answer these and above, or these above dependent? Are there more variables that we can use to answer these questions? And these are just a small number of questions. One thing that drives me insane, or that really gets my goat, is whenever I'm reading papers in bioinformatics where they use multiple linear regression to predict certain types of protein growth and certain types of protein survival, and they tend to just use one variable. I'm thinking protein growth and protein survival is extremely complicated. There's so many things. There's nutrition, there's stress, there's cellular stress, there's toxins, there's toxins in the environment. There are many different things that make proteins grow, and just having a model where we just have one thing might give us some kind of reason to believe that that's the thing, that's the variable that creates or that controls growth. But actually, it may not be that thing. It just happens to be coincidental. But actually, in reality, it is that there are other things. So those other things that you would have that would somehow influence your dependent variable, in this case, which is y, would be your x1, x2, x3, x4. These are all the different x's that you would have, which you would throw into an equation, and those would create this really bizarre looking line that's kind of curving and waving and moving all over the place. It's not necessarily a straight line anymore. It is a line, but it's not necessarily a straight line. But your independent variables in this particular line equation would be these x's, which are kind of strung out as terms in this line equation. Your dependent variable is still your y, and your independent is still your x. But you now have many different x variables to look at, lots of x's. And so your equation in this case here, you'd have like beta 1, beta 2, beta 3. These are all the different betas. Those are like the different slopes that we were working with before. Remember that y equals mx plus b that we were working with? That line equation? Now it's not just one beta, but it's a whole multitude of beta. Every x that we put into our equation has its own slope, if you will. And so we have many, many more things to work with. And that makes our math much more complicated, but that's okay. Luckily, we have R to help us get there, which is going to be really, really cool. But each of the variables that you're trying to test, though, to see how it influences your y, would go here. That's your first variable. Next one here. The next one there. I don't think it really makes any difference about the order just yet, about where they go in the equation, just as long as they're there, because you're just adding these terms together, so the order doesn't matter. But that they're there does make a difference. Anyway. Another thing I should say, though, is that we assume that that there's a normal distribution with the mean 0 and the constant variance, with a constant variance. What I mean by this is that we have to make certain types of assumptions for our models so that the models actually produce something that we can use. I don't have the slides actually here, but supposing, for instance, that the variables, one thing that you have to talk about there is like the variables are actually, they actually conform to some kind of normal distribution. In other words, when you plot these variables out, do you find that they kind of clump together in a kind of a predictable normal distribution on the plot? We don't actually talk about that too much in here because that also is an entire section of class. If we just talked about that, then that would be the other half of the class. So, but just remember though that when you are using these models, though, there are some assumptions that you have to go through. In other words, that your errors have a normal distribution, and you have a mean of 0, and a constant variance exists too. I think that R, in some cases, will complain if these are not met when you're trying to make your models. But I think there's under certain conditions. Anyway, I'm going to move on in the interest of time here. But the one thing I did want to talk about, though, is that we have the hypotheses to handle. We're talking about a hypothesis. Remember the null hypothesis and the alternate hypothesis? Well, remember before, just going back to this line equation, imagine that this is my line and this is my equation here. Imagine before my hypothesis was that this beta 1, which is my slope, was equal to 0. That was the null hypothesis, and the alternate hypothesis was that this was not 0. That means that there was something else happening here. This value was actually influencing my x. Oops, let me get the x here. That's right. So this beta 1 was actually influencing my x in some way. That was the alternative hypothesis. But the null hypothesis was that this guy was just equal to 1. And there's nothing happening. Oh, sorry, it's like equal to 0. And so there was nothing going on. It was just 0, 0. And so that means that when it was 0, that there is no influence over here. Nothing is happening. Things are changing now, where, for instance, now we have a null hypothesis, which is saying that all these b's that we're working with here, these busy b's, this b, this, oops, I get them here. This b, all the b's are all equal to 0. That is what my null hypothesis is all about now. So I'm thinking of in terms of slope. So my null hypothesis is that the b's are zeros, and my alternative hypothesis is that they are not zeros, which means that the alternative hypothesis, remember, is saying that something is happening. It's nothing. It's not nothing. There is something happening. My alternative hypothesis is that something is happening. The null hypothesis is that there's nothing happening. Nothing, null. Nothing is happening. alternative hypothesis, there is something going on. I don't know what it is, but there is something happening. So that is actually done by saying whether or not something's happening is you're really testing mathematically. Is that a zero? Is this a zero? Is this a zero? Is this a zero? Are my b's zeros? Are they not doing anything to my equation? If they're zeros, then my equation doesn't have any mathematical flexibility. It's not able to move. And so there's no effect. And so that would be my null hypothesis, that these b's are just zeros and nothing's going on. However, if I find that I can throw out the null hypothesis and embrace the alternative hypothesis to say that these b's are actually not zeros, they're something else, then that means that I can do something. That means I can say that there is some kind of influence between my variables and my y. Something is going on. They're playing. They're doing something. Something's happening. Now, of course, when I say something, that's a very vague way of saying that there is some kind of condition going on between my independent and dependent variables. The data is not going to tell me what that is. I have to actually get out there and look and see. But the data is suggesting that there is some kind of play happening or some feedback that's going on between the dependent variables from the independents. So if the null hypothesis were the case, then change the value of x1. If the null hypothesis is instated here, then nothing is going on between x and y. They're not related in some ways. Anyway, there's this you can look at. That's a lot of text. I'm sorry about that. But we're going to ask a question here, and the question is, do the variables age and height both influence the capacity of lungs? It makes sense, actually, though, because when I see, like, for instance, some of the older people, I remember my grandfather, when I was little, he and I moved a table from downstairs upstairs. He was a non-smoker. He didn't drink. He didn't do anything. But he was, like, huffing and puffing at the very, very top of the stairs for, like 5 minutes. I thought, what's going on with this guy? Is he okay? He's like, no, I'm fine. I just have to, it just takes me some time. I used to go out and have his runs and everything like that, but he'd just be huffing and puffing for some time. And there's nothing wrong with his lungs or anything like that, but just because I think he was older, his lungs didn't seem to recover as fast as mine. So once we got that table upstairs, and I was like, okay, let's move the chairs. And he's like, no, this is just let's just wait and see where this table can go and take some time and look at the carpet. And I'm like, no, let's go downstairs and do this thing. But there is so that part of my life, I thought maybe there is some kind of difference between age or some kind of capacity difference that happens with age. Like when you're getting older, your capacity changes. But anyway, this is the experiment that we're going to do here, where we're actually going to create a model, and we're going to see whether we can find out whether there's a variable or a coefficient for age and a coefficient for height that we can put into this into our model and use that model to make some kind of prediction. In other words, the older you get or the taller you get, does that change anything to do with your lung capacity? And if so, what kind of changes does it create? And so again, to do that, we're going to need data. So let us just grab this data here. And I believe that if you look at your, let's go back here. If you look at your, the data or the sandbox from today, I put the let's get my words here. But I put that the data set in there for you, so you should be able to find that. I'm going to go ahead and just remove this. Actually, where's my? Let's copy this because I'm lazy. Removing the old variables. Did I even start working with that? Lost it. I don't know where it went. I don't know where it went. I think it's going away. Okay, so what I'm going to do now is I'll just copy this in, and I'll have to edit this around. I don't know how else I can do this. Library is there. It's my lung capacity. Now, of course, I have to install my packages if they're not there, but they are there. So now I'm going to make, actually, what was my, oops, what did I call my data here? I called my data LC. That's what it was. There we go. So I go down here. Hopefully everybody is able to kind of like, you're just basically going back and forth from the code to the slides and making sure that everything looks exactly as it is. So now what I'm going to do is I'm going to run my RM, remove all the stuff remove all my variables that I've got. Then I'll just run these things, run my libraries. I have to find my file. So LC is going to be my lung capacity. I will find that in my sandbox from today and from last Thursday, I believe. Just lungs cap. Hopefully everyone found that. And then I have this line here where I'm going to be actually reading in the data, and I'll call that data lung cap. One thing I will say, by the way, is that when you're writing code that actually does read in, when actually you're creating a data set, you'll notice that this data set that I've just created is called data lung cap. I tend to use the word data to suggest that that's my data set. But then I have a couple of words after that that kind of describe what that data set is. Now, going through your, you should, I did grade lab, was it 3 last night, and I think the grades were up on Sakai. And I was looking through the code for many people when they're putting together their vaccine data, and they just use like, X as their data set. Now, while X is a perfectly fine variable, you can use that. And as long as you know what X is, but I would say that X is probably not the best name for a data set, because data sets tend to have like, they're used all over the place, and you might want to go back to your code sometime and revisit these things and to kind of like see how your code works. And so you might want to use variables that actually help you to read the code, and so using X is not very descriptive. So I'd call it something like, data lung capacity, so you know what that data is. But anyway, you can compute the way you want, but I'm just saying that it might save you some time in the future when future you is looking at your code and trying to determine what you wrote back in 2020. It happens to me all the time. I look at some of my code from like years ago, and I'm thinking to myself, why was I not more descriptive when I put together my data sets? In fact, I kid you not, one of my variables was one of my data variables that I was looking in code just from like last week was this thing. That was what I called data back in 2016. And that was just insane. What was I just want to go back in time and kick myself. Like, what are you doing? So don't be me, be you, and come up with better names for your data sets so that future you, when you look at these things, you're not like scratching your head thinking, what? Anyway, but still, this is where I am now. This is the data set. So I have lung capacity, I have age, I have height, I have whether they smoke cigarettes, I guess. Whether they are male or female, and cesarean. I guess if they're born by a cesarean, that's a C-section. So the lung capacity and the age and height, those are the variables that we're really going after. But we could still look at our data in terms of like the gender, or whether they smoke, or whether they were born as cesarean, and we can aggregate the data in those forms. So let me just go back to the slides and see what the next piece of code is we're doing. We're actually going to create a model. If you can all see this, I'm going to create my model and come back with me, if you will, to here. And I'll just dump this in there. And of course, my model doesn't. My code doesn't work the way it's supposed to go. Let me fix this. Model creation. Let's call it mod, I think. And then I'm going to have a reports. And I'm just going to make sure that this is actually, let me just go back and see. Yep, okay, so this is good. Do that. Running this, I've run my mod, and then, oops, I have the summary here. I can run a summary, and my summary, then, let's just take a moment here and look at the summary. Now, the first thing I look at, the very first thing I look at, is how much respect do I give this model? The p-value is tiny. So that means that it's going to be, it's significant. There is some significance here. So then the next thing I look at, after I look at my p-value, how much respect do I give it? It seems to be worthy. It seems like it's statistically significant because it's so close to 0. The next thing I look at is this adjusted R squared. Wow, 0.84. What are we thinking? We're thinking good. We're thinking good. That's like there's like 15 points of something missing. Actually, we're doing a pretty good job. We're explaining. That means that our independent variables explain very well our dependent variable. Oh, sorry, our dependent variables. Oh, sorry, independent variables are explaining dependent variables. Exactly. So that means that age and height are doing a good job of explaining the lung capacity. Now, one thing I should tell you, and that's what this is over here, lung capacity. One thing I should tell you, though, is that the more variables you have in your equation, you'll notice the better your model is going to get. So, for instance, here, with such a small p-value, I know that's in this day and age, when you're saying that something is tiny, that's better than something when something's big. But in this case, you want a small p-value. But because we have more variables in our model, we're actually getting a better description of what's going on between that or in that model. Our dependent variable is better explained by the independent variables that we use. And I would imagine that the more pieces of information we throw into this thing, which are relevant to lung capacity, then the higher this value will go to a point. Then you might find that you're just not finding the right variables anymore, and your model will have to be redesigned. But that's not bad, though. This is actually quite a manageable model that you could actually use to tell quite a good story. Okay, so I'm happy with that. We've got some good numbers to look at. Let's move on back to our slides and see what the old slides say. And in fact, here's the summary you can check out. You have the adjusted R² value. You have a good p-value. Everything seems to be going quite well. What I wanted to spend some time, though, in these slides, though, is kind of taking you through some of these other numbers in here. I promised you I would, and I think we're going to spend some time. In fact, we have about 7 minutes, and I think that we'll just hit these slides, and then maybe we'll be done with this slide deck. But I think the most important piece is just kind of like getting an idea about what these numbers are. So we've discussed the intercepts. Now, the estimated mean lung capacity of somebody having an age and height of 0, we can ask ourselves, is that meaningful? Well, we have to find out. In fact, if you're looking at the intercepts again, I would say to plot these, to plot out these two different scenarios and see whether, for instance, the model is saying that points are in areas where they're not. So you can ask yourself, you can create your model out of these intercepts here, these coefficients, and then create a line equation here, and then plot that with the data actually in the background, and see whether, for instance, your line is actually kind of going through many of the areas where the points were found. So there's that. But the thing is that these intercepts are actually these slopes. They're actually like the slopes. Remember, they're the slopes in the line equation. So, for instance, here the slope, if you will, of age. If age is the variable, the slope that would be attached to that, or the coefficient that would be attached to that as a term in the equation, would be 0.126. That's your equation variable. And the same for height, you'd have 0.278, I guess. And so when you're actually creating a line equation that looks like this is your age slope, and this is your height slope. And this is your variable you can change for age and height. Well, it's your model. That's your model's variable that you could use to test. That's your x you can throw in there. Your independent variable. Now you are looking at the how is my age variable related to height here? So what we can do now is we can look at these numbers. I'll just read this here. But the effect of age on lung capacity, adjusting or controlling for height. We may associate an increase of 1 year in age with an increase in 0.126 in lung capacity. So that means that when you're looking at 1 year in age, that actually translates to 0.126 in lung capacity, and that's what these numbers actually mean. And so I guess when you're looking at the age, the basic unit 1, actually in this case here translates to an increase in 0.126 in lung capacity. That's like that's how age is actually influencing your lung capacity. And the same thing for height. Your height is influencing your lung capacity by 0.278 in terms of the height there, in terms of 1 year in age. So anyway, that's kind of interesting here. We have all this information that we didn't really know that. I mean, what else can we do with this? You can do a whole bunch of things with these statistics now that you have them. Another thing that's important, though, is looking at this stuff on the side here. We have, for instance, the t-value, and then we have some other information that's on the right-hand side on the age line. So what is that? This is the age statistic. This is the age statistic that we can use to perform that the hypothesis is actually relevant in this case here. So for instance, that our hypothesis, remember the null hypothesis is that age is equal to 0. These 3 stars that exist after that 3.45 times 10 to the minus 12, that's your test statistic value here. But the 3 stars, in fact, I can't select this stuff here, but the 3 stars indicate that that is a significant value. It's significant. Where the red box is, it's significant. So that suggests to me, long story short, that age is actually a good variable to be putting into this equation. And same with height, because I have 3 stars after that. And that's suggesting to me that, again, it's a significant variable which is being put into my model, which is actually carrying some weight and allowing my model to have some extra power. And here we go here. Again, we have height, which you can see has 3 stars. The estimated effect on height on lung capacity adjusted for age. That's what just like we have, well, they're both significant here. And I have to move on here, just in interest of time here. The test statistic that we use to perform the hypothesis test for the slope for height equals 0. So again, we have a height test statistic. We have them for both age and height. So you can kind of see, when you're creating your model, you can see whether these variables actually have to be there. I mean, are they actually doing anything helpful in your model? And you can look at these, at this rundown here. Obviously, there's more to it than just this. There are other tests you can run to see whether your model is working out well, but this is it's a good predictor. And again, here we have, for instance, there are multiple r squared, but I always look at the adjusted r squared to suggest, which allow me to kind of like compare these tests, these models to other models, for instance, if I'm using other models for the data set, but I can use, I mean, they're both, you can use them both, I guess, but I always just look at the adjusted r squared. But again, it's telling me that, for instance, 85%, if you will, 84% of my model is being, of my dependent variable is being explained by my independent variables in my model, i.e. age or height. Down here at the bottom, we have the F statistic. If you had a giant table of values that you'd have to look at, that you'd use to, to judge the goodness of fit for your model, there's big tables where you have to look up like an F value and degrees of freedom. That's this value here. That's what this stuff is here. And so you could actually look this stuff up, and you can actually look up some of the p-value in some big statistics table. And so I think you never actually use this, but R actually always just puts it into the output just in case you need it. But a null hypothesis, though, don't forget, we're just saying that here's the all these different betas. These are all, we're just saying that the null hypothesis is that they are all 0. Everything is 0, and they're not doing anything to influence my y. And so, for instance, my null hypothesis is that there's nothing happening between my x and my y. Nothing's going on. It's just all the same. However, the alternative hypothesis is that there is something happening. But for the null hypothesis, just remember, though, that these are all zeros, all of them. Age is 0, the height is, the b for height is 0. They're all the slopes are 0. So that means that this beta 1, beta 2, beta 3, zeros. So the p-value here is very close to 0 in this particular model here. And so that we can conclude that there is something non-random happening in this model. The model is accurate. It's suggesting that something is going on. These variables are doing something. Age and height are doing something. Let me just finish up these last, how many more slides do we have here? Almost done with this. Oh gosh. I think we have to finish this actually next, this week, Thursday. But let me just finish up this one slide here, and then we'll break. I know that we're over time here. But we have this, let's see here. This is this residual standard error. I'll just read this. This error gives an idea about how far the observed lung capacity or the dependent variable values are from the predicted. So this is kind of like your residual, remember the residual value, the RSS values that we were talking about? Kind of like how far do the points fall from where the model actually is predicting that they do fall? So this is your standard error. We're talking about that. And so you can use these to look up, for instance, the distance, or you can use this, actually, I'll say you can use this to determine maybe the goodness of fit for your particular model. I think what I'm going to do is I'm going to end it here because we are a minute over, and so we'll talk about that when next we come together on Thursday. And so in the meantime, keep going strong here. I remember that, let's see, we have, Yeah, that's right. So yeah, no, I was going to say that we have this slide deck. Now I think that on Thursday we'll finish this, and then we'll go through a different slide deck. I would still like to talk to you about the one of the labs, like the vaccine lab that that you did for the class. And while that lab was, many of you did very, very well, I just had a couple of things that I wanted to talk about the lab, some of the take-home messages. And so I think we'll try and do that on Thursday, or if not, we'll do that on Tuesday of next week. Another thing I'd like to say, just is on your radar, we are going to be talking about the final projects, I think, next week. And also, we have a test coming up. Just let me just show you something here. All this will not be a surprise. I'll actually take some time to discuss everything with you. I'm going to data analytics. I'm going to be planning your time, and hopefully I can find it here. But I'm thinking that the test is going to be coming up on the, I guess on week 12 here. So that's like on the 7th, maybe the 17th, between the 17th and the 20th, in there somewhere. That's when we're going to have our exam too. But I will give you plenty of warning on that. And I'm thinking that, for instance, maybe that same week we'll talk about the final project, which you'll be doing for this course. Anyway, that's just coming up. Stay tuned, and we'll talk then. Everybody, stay well. I'll see you all very, very soon. Cool. What's that? It's not this week. No, the exam is not this week. The exam is not this week because we have a speaker. And I never like having exams from the speakers because I want you guys to be really kind of like just to listen to the speaker and like get involved in what the speaker is saying and kind of like just to pull everything in. So no, there's no exam this week. It's next week on this, I guess on the 17th, after the 17th. All right, rock and roll. Everyone stay well. I'll see you all very, very soon. Thank you. All right. This class is like coming to, it's coming to an end, isn't it? I mean, it's like we're